Welcome to Introductory Algebra Math 0420. In this video, we will be discussing Section 1.1, Introduction to Algebra, Variables and Mathematical Models. In this section, we will evaluate algebraic expressions, we will translate English phrases into algebraic expressions, we will determine whether a number is a solution to an equation, we will translate English sentences into algebraic equations, and we will evaluate formulas. Let's get started. Let's start with a definition. A variable, first thing we're defining is a variable. A variable is a letter that represents a variety of different numbers. So we can let X or Y represent a length, a width. We could represent a distance. We could represent a lot of different things just with a variable. Okay? So if we want to combine variables and numbers using operations, that's called an algebraic expression. So let's define that. A combination of variables, numbers, and operations is called an algebraic expression. Let's talk now about evaluating algebraic expressions. So as you saw in the last slide, an algebraic expression is a combination of variables and numbers using operations. Those operations could be addition, subtraction, multiplication, division, powers, roots, any number of things. Okay, so if we want to evaluate an algebraic expression, here are the steps. The first thing we want to do is to perform all operations with, let's rewrite that, all operations within grouping symbols, such as parentheses or brackets. Then we do all multiplications in the order they appear from left to right. And then finally, we do all additions and subtractions in the order in which they appear. Okay, so those are our steps. We do all the operations within grouping symbols, then we do multiplications from left to right, then we do additions and subtractions from left to right. Let's try an example. Okay, in this example, we want to evaluate each expression for x equals 10. So the first thing we'll do part A, which is 6 plus 2x. And what we want to do is we want to substitute the number for the variable. So what we'll do is we'll plug in 10 everywhere we see x. Okay, now we can evaluate We'll do the parentheses part first. You don't have to have the parentheses there, but that's just so we know that it's 2 times x or 2 times 10. So we do that first. So 6 plus 2 times 10, which is 20, and 6 plus 20 is 26. So that would be our answer in part A. In part B, we can plug in the 10 for x. We do have parentheses here. We can do that addition first. So 10 plus 6 is 16. So 2 times, in parentheses, 16. And 2 times 16 gives us 32. Okay, so that is how we'd find the answer in part B. It's how we would evaluate that expression when x is equal to 10. In this example, we want to evaluate each expression for x equals 3 and y equals 8. So we're stepping up our game a little bit, and now we have 2 variables instead of 1. So we have the expression in part A, 7x plus 2y. So we can substitute in each of the variables. So where we have x equals 3 and y equals 8, we can substitute the x equals 3 in for x and the y equals 8 in for y. So we say 7 times 3 plus 2 times 8. And we can perform those two multiplications. 7 times 3 is 21. Plus 2 times 8, which is 16. And then we do the final addition here, and that is 37. Okay, let's try another one. Same values for x and y, except now we have 6x minus y over 2y minus x minus 8. So we'll proceed in the same way. We'll plug in 3 for x and 8 for y. We have 2 times y, which is 8, minus x, which is 3, minus 8. Okay, so we'll do the stuff in the numerator first. 6 times 3 is 18 minus 8. We look in the denominator. 2 times 8 is 16 minus 3 minus 8. So 18 minus 8 in the numerator is 10. And then in the denominator, we have 16 minus 3. Left to right, remember, that's 13. 13 minus 8 is 5. So 10 over 5, 10 divided by 5 is 2. Okay, so that is evaluating algebraic expressions. Let's now move on to another topic, translating to algebraic expressions from English. Okay, many times when we're solving algebra problems, we will need to be able to translate from a word problem into an algebraic expression. So to help out with that, we have a table, which is also in your book on page 4, that has keywords that are related to addition, subtraction, multiplication, and division. So some of the keywords that mean addition, you may see the words plus, sum, more than, increased by. Subtraction, you'll see minus, difference, less than, or decreased by. For multiplication, you'll see times, product, twice, or multiplied by. And division, you'll see divide, quotient, ratio, or divided by. Now, these are some of the keywords. There may also be others that are related to these operations that you may see when you're doing word problems. Let's try some examples where we translate English phrases into algebraic expressions. In this example, we want to write each English phrase as an algebraic expression, and we want to let the variable x represent the number. So in part A, we want to find in an algebraic expression the product of 6 and a number. Well, we have 6 times our number x, and that's all we need to do for this one. For part B, we have a number added to 4. So that we have 4, and then we add that number x, so we get 4 plus x. For part C, 3 times a number increased by 5. So we have 3 times x, 3 times a number, increased by 5. That's a keyword for addition. So we'll add 5. D, we have twice a number subtracted from 12. So we start with 12 and we subtract 2 times a number. Well, x is our number, so we get 12 minus 2x. And then finally, E, the quotient of 15 and a number. So how would we write this? (15 over x), and that's the end of this example. Now let's talk about equations and determining whether a number is a solution of an equation. We first need to define what an equation is. An equation is a statement that two algebraic expressions are equal. You will always see the equal sign in an equation. So if it doesn't have an equal sign, it's not an equation. One more definition here. Solutions of an equation. Solutions of an equation are values of the variable that make the equation a true statement. So how do we determine whether a number is a solution for an equation? Well, what we would do is we would take that number, plug it into the equation, and see if we get a true statement. Let's try an example where we do just that. Okay, in this example, we want to determine whether the given number is a solution of the equation. So in part A, we have 9x minus 3 equals 42, and we get x is equal to 6. We want to check to see if x equals 6 is a solution. So we plug in 6 everywhere we see an x. And so we get 9x minus 3, or 9 times 6 minus 3. 9 times 6 is 54. Minus 3. 54 minus 3 is 51. Is 51 equal to 42? 51 is not equal to 42, since 51 is not equal to 42. X equals 6 is not a solution to the equation. Write that. To the equation 9x minus 3 equals 42. Okay, let's try another. In this example, we have 2 times the quantity y plus 3 equals 5y minus 3, and we want to plug in y equals 3 to see if that's a solution. So we plug in 3 everywhere we see a y. Okay, so on the left-hand side, we have 3 plus 3 in parentheses, so that turns into 6. And then on the right-hand side, we have 5 times 3, which is 15, minus 3. On the left-hand side, 2 times 6 is 12, and 15 minus 3 is also 12. When is 12 equal to 12? Well, 12 equals 12 every single time, and so y So since we end up with a true statement, y equals 3 is a solution to the equation 2 times y plus 3 equal to 5y minus 3. Now we need to talk about translating English sentences into algebraic equations. So earlier in the section we talked about translating English to algebraic expressions, but now we need to talk about translating English into equations. So we need to talk about words that can be standing in for the equals sign. Well, some words that we might see are equals, gives, yields, is the same as, and is, was, or will be. Anytime you see those words, you can insert an equal sign into your equation. Okay, so let's try an example where we translate English sentences into algebraic equations. In this example, we want to write each sentence as an equation. Let the variable x represent the number. In part A, the quotient of a number and 6 is 5. Remember that is represents the equal sign. So the quotient of a number, x, and 6 is equal to 5. Okay? So that's the equation that we needed to find in part A. In part B, we have 7 decreased by twice a number yields 1. So 7, and then we decrease by twice a number, yields, which is equals 1. So that's our equation in part B. So now we need to talk about evaluating formulas. So one of the things that algebra allows us to do is to make symbolic descriptions of phenomena that we see in the world. Descriptions of the world involve the use of formulas. A formula, let's define that. A formula is an equation that expresses a relationship between two or more variables. So the process of finding formulas, another definition here, the process of finding formulas to describe real-world phenomena is called mathematical modeling. And those formulas that we find as a result are called mathematical models. Let's do an example. Okay, In this example, example number 6, which is our last for this section, the bar graph shows the average price of a movie ticket from selected years from 1980 to 2010. The mathematical model that approximates the data by the bar graph shown below is the equation t is equal to 0.17n plus 2.46, where t is the average ticket price and n is the number of years after 1980. So if you look at the graph, you'll see the various years and the price of a movie ticket in those years. In this problem, we want to use the formula to find the average ticket price 10 years after 1980 or in 1990. And we want to find out if the mathematical models underestimate or overestimates the average ticket price shown by the bar graph for 1990, and if so, by how much. So for part A, the first thing we want to do is we want to use the 10 that we see here, and we want to plug that in for which variable. Well, it's 10 years after, so n is equal to 10. So n equals 10. So t, the ticket price, is equal to 0.17 n, which is 10, plus 2.46. Okay, we can evaluate that. That's 1.70, that's 0.17 times 10, plus 2.46. And if we do the math on that, what do we get? 1.70 plus 2.46, that gives us 4.16. So the model says that we should get 4.16 or $4.16, but in reality, the number was 3.75. So since our model is higher than the estimated value, or not the estimated, but the actual value, the model, spelled model wrong, M-O-D-E-L, the model overestimates the average ticket price and by how much? Well, we need to take 4.16 and subtract 3.75. We do the math on that by 41 cents. Okay. And for part B, the same thing. Our n in this case, we want to see does the mathematical model underestimate or overestimate the average ticket price shown in the bar graph for 2010. So how many years is that after 1980? Well, it's 10, 20, 30 years, so n equals 30. So t equals 0.17 times 30 plus 2.46. 0.17 times 30 is 5.10, not equals, but plus 2.46, which gives us a total of $7.56. And what was the actual value for 2010? It was 7.21. So the actual was 721. So again, we overestimate by, and we can subtract those. By 35 cents. So it actually is a closer estimate that far out, but it's still overestimating the average ticket price. Okay, that concludes all of the content for section 1.1. Please let me know if you have any questions over your homework, and I'll look forward to seeing you in the next one.